A fragment of plastic netting floats just beneath the ocean's surface. At first glance, it looks lifeless. Zoom in. Under a microscope, its surface isn't smooth. It's textured, layered, and densely populated. This is the plastisphere, a microbial community colonizing synthetic polymers in aquatic environments. Plastic in the ocean becomes a surface. Within days, bacteria, archaea, fungi, and microalgae form biofilms on it. By the end of the first week, microbial consortia can already be seen developing, organized into dense biofilms that are metabolically active and dynamic. Why does this matter for plastic degradation? Because individual microbes often fail in real-world conditions. But in the plastisphere, degradation is amplified by cooperation. One species can initiate oxidation of the polymer. Another can hydrolyze the resulting fragments. The microbial diversity increases the range of enzymes present: oxidases, hydrolases, esterases, enabling a broader attack on the plastic surface. The biofilm also protects the community from environmental stress. It buffers against salinity changes, UV exposure, and pH fluctuations. This stability allows long-term metabolic activity even in challenging marine conditions. Let's talk numbers. Bacillus cereus alone can degrade polypropylene microplastics by about 4% in 40 days. But when polypropylene is colonized by marine plastisphere communities, that number jumps to 11% in the same time frame, nearly 3 times more. Pseudomonas putida degrades polyurethane foam by 25% in 30 days. But when co-cultured with fungi in conditions similar to those found in plastispheres, degradation increases to as much as 40%. Even polystyrene, one of the most resistant plastics, shows changes when covered by plastisphere biofilms. In tropical marine environments, plastic fragments showed increased oxidation, up to 60% more surface carbonyl groups compared to sterile control samples. These results don't come from isolated enzymes or optimized lab conditions. They come from natural microbial communities working together. Several mechanisms explain this enhanced degradation. In most cases, plastics first undergo environmental oxidation through UV or heat. Then, the plastisphere continues the job, secreting enzymes that penetrate and fragment the weakened polymer. Scanning electron microscopy shows that biofilms infiltrate cracks in the plastic, accelerating microfragmentation. Metagenomic studies reveal that species within the plastisphere can exchange genes, including those coding for plastic-degrading enzymes. This lateral gene transfer increases enzymatic diversity and adaptability. And as microbes metabolize the plastic, they release acidic byproducts that lower pH around the surface, further aiding hydrolysis. This effect varies by plastic type. Polyethylene and polypropylene degrade significantly faster in plastisphere conditions, especially in warm, oxygen-rich surface waters. Polyurethane and PET undergo partial depolymerization, often requiring cooperation between fungi and bacteria. Polystyrene shows the most resistance, but surface erosion and oxidative pitting increase after 180 days or more of biofilm colonization. Plastisphere communities form not just in oceans, but also in estuaries, freshwater lakes, and even in wastewater systems. Their activity is strongest where the temperatures exceed 15 degrees Celsius and oxygen is abundant. In summary, the plastisphere increases plastic degradation rates by factors of 2 to 5 depending on polymer type and environmental conditions. It's not just the sum of its microbial parts, it enables new metabolic pathways through cooperation, niche sharing, and chemical synergy. And it expands the range of plastics that can be degraded in the wild, especially those that resist single microbe attack. Plastic-eating microbes are just the beginning. Up next, worms with stomachs strong enough to digest styrofoam,